Thank you. I'd like to thank the organizers and everybody else who is here. It's my first time in Brazil so far. The experience has been rather pleasant, so thank you very much for organizing this event. What I would like to tell you is a story that I worked on with these people, with Tobias Meng, Adolf Grusche, and Jens Bardersen, that we started when I was spending a few months at the Max Planck Institute in Dresden. And what I would really like to title this talk, instead of fractional chiral semimetals, is fractional Weil semimetals. But in all honesty, I would have to put that question mark, and hopefully towards the end I'll mention why that requires a question mark there. Now, Weil semimetals are very interesting. In my opinion, a very interesting phase of matter. We've heard last week from one of the speakers that there are no topological metals. I think Velevik would take exception to that, but probably the rest of us would more or less agree with that statement. However, Weil semimetals are not exactly metals, and they're definitely topological. So since I use the word Weil, let me just show the picture of Weil. Everybody is sick of pictures of Majorana, but probably not as many people know this. Actually, the only reason I brought it up is I like this quote. You can read it on your own time, but I think it's the proper expression of, for a theoretical physicist. What Weil has done is he looked at the Dirac equation in the case of the mass of fermions being 0. And he realized that in this case, the Dirac equation actually block diagonalizes into 2 by 2 equations. And these equations are written now in this form. And in this case, what you get is basically 2 copies of a semimetal with linear spectrum with different values of p dot sigma, which is helicity, quickly often misquoted as chirality in this business. But in any case, that's a conserved quantum number, and that characterizes the 2 Dirac cones that you obtain, or Weil cones, I should say, that you obtain from here. Curiously enough, the idea that Weil semimetals or Weil cones appear in condensed matter setting is also quite old, and it's due to Conyers-Herring, who realized in 1937 that if you have a generic band structure and you have an accidental crossing of 2 bands, then basically this should be described by Hermitian 2 by 2 Hamiltonians, where the 2 by 2 structure is simply corresponds to 2 bands you're dealing with, and that being a Hermitian Hamiltonian, it can always be written as basically a combination of identity and sigma matrices. And now, once you've done this, you can expand these coefficients around the crossing point, and by expanding them, you realize that, well, the crossing point is actually exactly a Weil point, perhaps not isotropic, but nevertheless it has the same basic structure. Now, it's only recently that people realize that this coefficient A, which is the coefficient in front of the identity matrix, should not be ignored. In fact, it can give a tilt to the whole spectrum, and that led to thinking of so-called type 2 Weil semimetals, where this Weil point can actually be covered by the fact that the other band just bends above it. Now, with that, I should quickly say that there was a recent, quite a bit of recent activity in this subject, in particular experimental activity, and people now believe or have strong arguments for why certain types of materials are so-called Dirac semimetals, and I'll tell you what the difference between Dirac and Weil is. And even more interestingly, these 2 materials are strong candidates for Weil semimetals. Now, just to tell you, well, a proof of the fact that the subject is catching up is corny jokes by other physicists that get published in various journals. I take no responsibility for those, so I'll just go forward. Now, what's so topological about Weil semimetals? So once again, this is a picture, naive picture of a Weil cone or Weil point. And the Hamiltonian, at least near this crossing point, is described simply by p dot sigma, where p is momentum, and sigma is a combination of Pauli matrices. Whether or not that's real spin or not, that kind of depends on the system you want to consider, but that's that. That's the Hamiltonian that you have. Now, one thing is that, well, this is a purely band structure effect, and you can calculate the Berry curvature associated with that structure. And what you would find is that a Weyl point is actually a monopole of the Berry flux. And that automatically means that you can't have a single one in a Brillouin zone. Since that one has no boundaries, and that mandates the fact that there is another one somewhere else. So if you have a monopole, you have a Dirac string that originates from that point, but it has to terminate somewhere within the Brillouin zone, which is a compact manifold, and so there has to be an oppositely charged Weyl point somewhere else in the Brillouin zone. And that's actually the whole content of this famous theorem by Nielsen and Ninomier that claim that you can't have a single Weyl point or a single copy of a chiral fermion if you put them on the lattice. Putting them on the lattice means that you have to produce a Brillouin zone. That's, in short, that's what's topological about this. This actually has some rather interesting consequences that I want to mention in a second. But before I go there, I'll mention that, well, as I already said, the minimal model of a Weyl semimetal necessarily contains two Weyl nodes, but actually their number is restricted by the kind of symmetries that you might have. The minimum number of those Weyl points is restricted by the symmetries that you might have in your model. And it's kind of useful to very quickly review what those symmetries are. If you have inversion symmetry, then, so Weyl semimetals necessarily break either time reversal or inversion symmetry, or in principle they can break both. So let's just ask ourselves, what if we have inversion symmetry? If we have inversion symmetry, then basically the inversion symmetry maps k to minus k. It doesn't do anything to the spin quantum number, and so the energy obeys this rule. And so if you imagine having one Weyl cone somewhere off the gamma point in your Brillouin zone, and do the inversion operation, you realize that you actually produce another Weyl point on the opposite side of the gamma point, which has the opposite Berry charge, monopole charge. And that's easy to see because a spin up here gets mapped onto the spin on the opposite side of that gamma point, and it's the same exact spin as prescribed here. And so what you do is you produce this, the two copies of oppositely charged, well, so produce one copy of two oppositely charged Weyl points. On the other hand, if you have time reversal symmetry, that mandates that k goes to minus k, sigma goes to minus sigma under the time reversal symmetry operation, and the energy of spin down becomes the energy of spin up. And so now if you try to play the same game, you realize that if you take one Weyl cone and ask yourself, well, where's the other one is, by applying this time reversal symmetry, you obtain another positively charged point, and that is easy to see because the spin over here gets mapped onto the negative spin over there, and just comparing these two pictures, you see that both of them have the same charge. And so what you need is two other Weyl points in your Brillouin zone, and so if you have time reversal symmetry, then you should have at least 4 Weyl points. Finally, if you have both symmetries, then what you have is a Dirac semimetal, which is, you should basically think as two copies of Weyl semimetal sitting on top of one another. So that said, let me say, so you have to then look at some other quantum numbers that prevent basically Dirac string looping back to the same point. And so the topological nature of Dirac semimetal is not obvious from the considerations I just gave, and let me not go into this very deeply. But for Weyl semimetals, it's definitely the case because for Dirac you just put sources and sinks right on top of one another, so you need. Yes. So that's exactly the point. You need to start thinking about other quantum numbers that prevent this from happening. All right. So now, since I already mentioned that Weyl points are sources and sinks of Berry flux, there is a Dirac string associated with that. You realize that you can detect that by taking cross sections in your K space, and these cross sections will actually know whether or not there is what is the number of Dirac strings that crosses them, and that's a topological invariant. Even if you bend the Dirac string, nothing changes because this is a topologically trivial plane. You get a plus and a minus one flux going through, and this one is topologically non-trivial. And the immediate consequence of that is that if you start thinking about the band structure, depending of where you put your cross-section, that is, let's say, the value of kz that you fix, you would have, in both cases, a gapped spectrum for a fixed value of kz, but in one case it would have a non-zero Chern number, in the other case it will have a zero Chern number, and so you have topologically distinct parts of your Brillouin zone from that point of view, and that so that reflects in the fact that what you actually get. Oh, sorry, I guess I'm missing a slide. So that reflects itself in so-called Fermi arcs that you find on the surface of Weyl semimetals. But I don't want to talk about this any further because, well, after all, what I'm going to tell you about has nothing to do with the band structure. These are so far have been non-interacting band structure effects. Now, the one topological feature that is not related in any obvious way to the band structure is a so-called chiral anomaly, or helical anomaly, if you want to be precise. And that is the fact that if you have two Weyl cones, you can imagine depleting one of them, and of course, if you have a conserved number of particles, you have to put the electrons into the other. And what you find is, as I said, for a conserved number of electrons, the total number of particles is conserved, but the difference between the occupancies of these 2 points is not conserved. And in fact, not only it's not conserved, it's actually quantized. And that's the statement about this chiral anomaly. So most of you are probably more familiar with a one-dimensional version of a chiral anomaly, where you have simply one-dimensional liquid-like spectrum, and what you can have is you can have the situation where you apply the external electric field, and that leads to either increased or decreased occupation of the of this branch of the spectrum. Now, naively, that would think, well, so the change of momentum, the derivative of momentum with respect to time becomes non-zero, so and the momentum is immediately connected through the density of states through to the occupancy of electrons on that branch, and you find a rather unphysical result that by applying the electric field, you change the occupation of that branch. But of course, that is resolved by the fact that there is another branch with the opposite chirality somewhere else in the spectrum, and so you simply take electrons from one branch to the other, like it's shown here, for example, but nonetheless, this fairly transparent effect is known as chiral anomaly in the condensed matter setting, anyhow. In the Weyl case, it's similar, except this, the rate at which the occupancy or the difference between the two occupancies changes is not just proportional to the electric field as it would be in one dimension, it's proportional to E dot B, and the coefficient in front of it is quantized, just like it was in the 1D case. The quantization coefficient is somewhat different, but nonetheless. So in order to understand where this comes from, the easiest place to, well, so in principle, if you want to be more physical, you would also include a term that relaxes the occupations of two different periphases, which is important if you actually do some calculations, look for the consequences of this effect. But let me now just very quickly comment on the origin of this anomaly, and that's easiest to understand if you actually start looking at this at a very strong magnetic field. And so if you just look at the non-interacting simple Weyl Hamiltonian given by spectrum is basically encoded here, and expose it to a very strong magnetic field such that you actually quantize the spectrum and get Landau levels, you go through the standard exercises of writing creation and annihilation operators, nothing new here, that with that, you can write the Hamiltonian in this matrix form. And what you find out is Landau levels, except there is one special Landau level that corresponds to n equals 0. And if you stare at this energy, you realize that that 0th Landau level is linearly dispersive. And whether it's tilted to the right or to the left is actually determined by this value of kappa, which is plus or minus 1. That's the chirality or helicity, I should say, of the Weyl cone from which it came. And so since you have at least 2 Weyl cones, you get 2 chiral, one-dimensional like liquids here. And I already know everything about one-dimensional cases that I wanted to know. In fact, I've just shown you a caricature before, and I can just, well, in principle, they're connected somewhere within the spectrum, of course, but I could just copy the results from the one-dimensional case, and that is the change of momentum is proportional to the electric field. That's just the rate at which you pour the electrons from one side to another. But this time, the occupancy of each of these branches is not just given by whatever pi 2 pi h bar states per one state per 2 pi h bar of momentum. It's actually a Landau level, so it has huge degeneracy that is proportional to the magnetic field. And once you account for this degeneracy, you produce this E dot B. So E is what drives the discrepancy, and B is the degeneracy that is associated with that. And that's that. So that's the origin of the E dot B term. All right. And so that actually, there was a number of papers that were looking for different interesting consequences of having this chiral anomaly. I should just say that was one which is very transparent. It's a quasi-classical treatment of a Weyl semimetal, and the quasi-classical treatment is basically solving a usual Boltzmann equation, with the only difference is that this time there appears to be one extra term to the semi-classical equations of motions. That is the anomalous velocity, which is a consequence of having a Berry curvature in your system. And once you do this, you actually find out a rather interesting result, and that is you get this positive contribution to the diagonal conductivity, which is quadratic in B, and so it's positive so it's a negative magnetic resistance. It's positive magnetic conductivity, if you wish, that is quadratic in B, and that has been seen in thallium arsenide. It's still a question whether or not this positive magnetic resistance is really a consequence of the Weyl nature of this metal, but I'll just leave you with that. So, all right. So now I'm actually having burnt like about half of my time. I'll turn to the work that we have actually done. So what we were interested in is, so far everything I told you about was based on the band effect, or at least can easily be understood based on the band structure. What we were interested in is whether or not there is such a thing as an interacting Weyl semimetal, where you can't really meaningfully talk about any band structure, or even further, is there such a thing as a fractional version of that? And I'll define that statement precisely a little bit later. But first I should say that there were, the way we proceeded, there were 3 main sources of inspiration for us. The first one was a paper that was published by Sucheng Zhang and Jingping Hu back in 2001, which constructed a 4+1 or 4-dimensional quantum Hall state. Turns out you can construct quantum Hall state in any even number of spatial dimensions, not just 2. It also works in 4 dimensions. And quantum Hall state is a gap state in the bulk, so you can ask yourself, well, what's the surface of that bulk state? The surface being 3-dimensional, that is in real space, you find that the surface is actually a chiral metal. It contains a single Weyl cone on the surface of that. And so that already gives you an idea of what a fractional Weyl metal might be. So a naive place to look for is to look at the surface of a fractional 4-dimensional quantum Hall effect. And well, we were slightly more precise than that, but that's just one piece of inspiration. The other piece of inspiration is a construction, a 2+1 dimensional construction of quantum Hall states by actually taking 1+1 quantum systems, that is quantum wires, and coupling them together. And that was done in 2002 by Kane and co-authors, and I'll comment on how it's done. And then there is the Third, rather interesting piece of work that appeared rather recently, it's by people from the Weizmann group, and what they showed is how to actually get a Chern-Simons theory from these from the wire construction. So now let me actually very quickly review the second point here, and that is the Kane work. So the idea was fairly transparent, and what they did, what Kane and co-authors did, is they looked at a series of quantum wires, which are identical, and they're exposed to the external magnetic field. What you should do, or what you can do, is look at them in the Landau gauge, where momentum, K, quasi-momentum, is actually a good quantum number along the wire. And so each wire has the same identical parabolic spectrum in terms of that momentum. But what changes between the wires is that the presence of the vector potential, because of this magnetic field, actually shifts these parabolae with respect to one another. And so then you can ask yourself, well, how can you possibly open a gap in a series of these wires? And the most transparent way of opening the gap is just look at the crossing points between these parabolae. And if there is any tunneling between the wires, that would naturally open the gap. And since you know at what value of energy and therefore concentration that happens, and what is the magnetic field corresponding to that, the magnetic field is responsible for shifting these parabolae with respect to one another, you can actually very quickly figure out that these are the integer Landau's, the integer quantum Hall states. And so what you get is a gap bulk, and you get also H states from the fact that the very first and the very last parabola have their left and right branches that cannot be gapped by this mechanism. So that's nice, but then you can ask yourself, well, what about nu equals 1/3? That sits presumably somewhere here, and there is nothing obvious that would open a gap there. Turns out there is a mechanism that opens the gap here. In fact, there are many, that being 1D, you can actually beat it to death by analyzing what kind of instabilities you can produce in these systems. And in particular, Kane and co-authors identified instability that would stabilize a nu equals 1/3 quantum Hall state. And that is an interaction between these wires where one electron would hop from one wire to another, and since you have to conserve momentum, since you have to conserve momentum, you would have to send two other electrons backwards within each wire, and that actually stabilizes this nu equals 1/3 quantum Hall state. You can you can easily do that for the entire Laughlin series. And moreover, this construction has been recently utilized for various other topological states, for non-abelian fractional quantum Hall states, for spin liquids, for 3D topological insulators, and one particularly interesting piece that we kind of rely on that even derives a Chern-Simons theory from that construction is the last reference here. And I probably missed a few other references. All right, so now what we want to do is we want to do basically the same thing, except we want to construct a 4-dimensional topological state out of 3-dimensional quote-unquote wires. That seems like a crazy idea, and it probably is, because I really don't know. So the hope would be is that I take my non-interacting states of matter, quote-unquote wires. Each of them is a non-interacting vial semimetal with two vial cones, and then I somehow find how to turn the interactions on in such a way as to actually gap out all the internal pairs of vial cones, leaving myself with two copies of vial cones on the front and the back side of my 4-dimensional sample. So what lives here is still a 3-dimensional object, and in the same exact way in which the wire construction gapped the 2-dimensional bulk, leaving the 1-dimensional chiral states on the sides of the 2-dimensional bulk. So now, but as I mentioned, I really don't know how to do it with 3-dimensional objects, so it would be nice if I knew. But since I don't know how to do it honestly, I'll cheat. how will I cheat? I'll reduce this problem to the problem I know how to handle. That is one dimension. How will I do that? I'll just turn a very strong magnetic field along one of the real spatial dimensions, let's say Z. And that will, as in the slide I've shown you before, that will actually create Landau levels, except there will be one remaining linearly dispersing Landau level that was left of each of the codes. And I'll focus on what happens here, ignoring the existence of higher Landau bands that are very high up in energy. So I'm working in the limit of very strong quantizing magnetic field in the Z direction. All right, so now I look at these, well, basically one-dimensional chiral state because the motion in the X and Y direction has been completely quantized. So the only, basically recognize the picture that I've seen before, the only difference being that now each of those dispersing, linearly dispersing branches carries huge degeneracy. But so what? So now I will just focus on these linearly dispersing branches, and I'll just follow step by step almost exactly the Kane, Lubensky, and Muhabbadeh program of constructing, of gapping those out. So and the next couple of slides are purely technical, so those of you who are familiar with Bézénization, by all means I'll walk you through some main steps. Those who are not can probably safely ignore the next couple of slides. So what you do is now you have from each copy of your non-interacting vial semimetals, what you are left with is two linearly dispersing branches, and each of them is described by well, the left and right moving particles, where the actual electron operator is written in terms of both left and right movers, and B here is just the momentum, it's the momentum difference between the locations of the two vial points. So the next step is to bosonize these fields, and once you've done this, you get a bosonic Hamiltonian that describes all these copies of the right and left movers. So that's fairly standard. And then the last point is to identify the interactions that will actually gap those internal degrees of freedom. By that I mean the internal linearly dispersing branches. And in order to do this, you identify the type of interactions that you want to impose here, and the interactions are actually, well, are going to be exactly the same as before. So what you want to have is you want to have a normal tunneling of electrons between the two branches. So that's the type of interactions that typically opens the integer quantum Hall gap. But on top of that, you also want the other type of interactions that are responsible for the fractional gap, and that is one electron moving between the two quote-unquote wires, three-dimensional wires, and in order to conserve momentum, you also have m electrons, where m is any integer hopping within the wire from the right moving branch to the left moving, in this case, from the left moving branch to the right moving branch. And with a simple change of variables that is suitable for that process, what you can do is you can, well, so far it's just mathematics is change of variable. You identify the tunneling term that corresponds to this process is basically a cosine that can be easily written in terms of these new variables that we introduced, and at particular values of momentum shift and filling, this cosine is the most relevant perturbation in your theory, and it opens a gap just like it did in the Kane, Muhabbadeh, and Lubensky case. And if that happens, then so if this cosine is the stronger, is the most relevant perturbation, it just fixes the difference between these fields, these new fields phi tilde, to some multiples of 2 pi, and by doing that, it actually gaps all the internal branches, leaving the external branches exposed in some sense. And so what you have is you have chiral metals that are left on the two sides of your four-dimensional sample, and what we conjecture is that these two copies of chiral metal are actually fractional chiral semimetals. And what's fractional about them is actually worth exploring, and that is what I'm going to do in the remaining, whatever, 5 minutes I might have. I'll tell you right away what's fractional about them. The fractional thing about them is the electromagnetic response that you can actually work out using the trick that I'll show you, and it shows this normal, what did I do? Sorry. It shows this normal looking chiral anomaly, except the coefficient in front of it is not the old e cubed over 4 pi squared, but it's that thing divided by 2m plus 1. For example, with m equals 1, then this is 1/3 of that, 1/5, and so on. So you get fractionalized or fractional response, electromagnetic response. And that, in a sense, can be used as a definition of what a fractional semimetal, a fractional chiral semimetal is. The way it's done is there is basically following the program that was outlined in this last paper that I called the last piece of inspiration, that allows us to actually generate the Chern-Simons theory out of this wire construction. And you do that by saying that, well, you have an action that is an action of fields and your gauge fields that went into your construction. And for convenience, I'll separate A4, that's the field that shifted parabolically with respect to one another, and the normal 3 components that produce real electric and magnetic field. After all, I'm interested in 3-dimensional, not 4-dimensional case after that. And so what are the pieces? One of the pieces is, well, that just contains the matter field, the electron field, so I'm not really so interested in that piece of my action. This piece of action is basically this bunch of cosines that are shifted with respect to one another by by A4, and then I also have this piece that couples matter to the gauge potential in the other 3 directions, which I just do by imposing the minimal coupling term, that is J times A. Now, one more piece of information is that my J, my physical current, should be conserved, and if I rewrite that, so if I rely on the fact that I can actually express the density in terms of my matter field, and then that allows me to rewrite the other components of my current in terms of the matter field, as I did here, and this relation that is actually a consequence of my variable change would automatically give me this fractional coefficient in front of that term. And so once I've done this, I do one last step, and that is I know that if I'm well in the gap phase, and that is the phase where the argument of my cosine is actually pinned to, well, let's say 0, to pi for that matter, it doesn't really matter, that actually allows me to get rid of this term by replacing it by A4. And once I've done this, so that's the statement I've made. Once I've done that, I find that my action can be written in terms of, so there is this the term that contains gauge fields and no matter fields at all, and with that, I can actually just, from this term, I can read the electromagnetic response right away by noticing that the sum over momenta, that's the sum over my wires, is actually nothing other than Landau level degeneracy that automatically generates B in the 3rd dimension. That's the one I used. And this would contain simply the electric field in the 3rd direction. And so the current that I can read from here is just that. So this is naked plane chiral anomaly obtained without any cheating from my construction that has this fractional coefficient. I can do slightly better than that, and by slightly better than that, I can actually try to, well, okay, so there is a little bit of a stretch, but I can try to recover full Chern-Simons theory. Because what I have just obtained is the expression that I can rewrite with changing B3 into the corresponding derivative of the vector potential. That's the expression from the previous slide, just written in terms of derivatives or vector potential and the derivatives. Now, what I notice is that action written like this is not gauge invariant. It's not gauge invariant for for an obvious reason. I broke gauge invariance by hand, by choosing the direction in which my magnetic field is pointing and so on. And if I wanted to get a full-blown Chern-Simons action, which is gauge invariant, I would look for an expression like this. Now you eyeball these two expressions, you compare them, and you realize that this is actually, so this contains some of the terms, but not all the terms that are present in the full-blown Chern-Simons theory. So therefore, you can then actually take this slight leap of faith and said, well, if I didn't break gauge invariance by hand, I would deserve all the terms, not just the parts that I collected in the theory where I broke gauge invariance by hand, and then you would just obtain, oops, what has just happened? My apologies. I'm almost done. Anyway. Right. So this is where I was. So you actually, by arguing that you deserve, that if you deserve fully gauge invariant theory, then this is the theory that you must produce, the theory that is four-dimensional Chern-Simons theory, and its response, its electromagnetic response, would be precisely of that form. That's the fractionalized version of a chiral anomaly. So with this, I should actually thank my collaborators. These are Tobias Meng, Adolfo Grushin, and Jens Barderson. I presume, well, except for Tobias, everybody doing what they like doing. So I'm in Brazil. Presumably people here love soccer, but they might not know that that much about European soccer, where Iceland actually made it as far as the quarterfinal of the European Cup. And this is Jens is from Iceland. As you might actually see, this is the picture he took of himself during that quarterfinal game at Stade de France, where presumably a very non-trivial percentage of the adult population of Iceland were in one place at that time. So finally, and I believe I still have 1 minute, or not? Yeah, without, okay. Well, that's fine. I'll just put the summary that has more question marks than anything else, and I'm willing to take questions.